Hello, everybody, and welcome to the new Sparring Partners. And today we're going to talk about backhaul, fronthaul, xhaul, anything that connects the RAN to the rest of the network. And I'm very glad to talk about it because I've been doing a lot of work on it in the past, but I have not done any podcast on it. And this is kind of interesting that when I started doing the podcast, I thought I'd run out of topics pretty soon because how many topics are there to talk about? But it turns out that there is so many that I can still cover without any risk of repetition. And with me today, I have Andy Sutton, and he is the BT Fellow and Principal Network Architect for Network Services at the BT Group. And he has been working on this forever. I've known him forever as well. And he's also teaching on it. So he's also working on the research part. And he has not only a huge amount of knowledge, but also experience because we've seen it's not just 5G. It's from when? 1G, 2G, 3G, all the Gs.
I started with 1G in the mid-80s. Yeah.
And throughout all the Gs, he's always been at the forefront of innovation. So, Andy, welcome so much to the podcast.
Hey, Monica, thank you very much. I appreciate the invitation. I'm really looking forward to our conversation today.
Me too. And before we get into the conversation, why don't you tell the audience who you are, what have you done for all the Gs and the coming Gs?
Yeah, sure, absolutely. Well, hello, everybody. Andy Sutton. I'm a BT Fellow and the Principal Network Architect for Wireless Access with BT Group. In that role, I'm responsible for aspects of the kind of wider RAN architecture evolution, including mobile backhaul or mobile xhaul, maybe as we should call it nowadays, and we'll explore those terms as we go through today's conversation. I also look after satellite communications in terms of not just mobile backhaul, but our broader satellite business for LEO and GEO. And I look after point-to-point microwave radios, again, used in backhaul, but also used in our broader kind of fixed network applications. So anything to do with wide area wireless really kind of comes across my desk. I've worked in the industry for about 40 years now, mainly in mobile and a lot of that in transmission and in backhaul, but also a lot of kind of wider kind of mobile strategy stuff as well. So as Monica says, I've had some experience with all of the Gs, from providing backhaul for analog tax systems right the way through to being involved with the introduction of GPRS when we really started to change the GSM network and introduce data. Of course, data is the norm now on all of our networks, through the 3G process and the use of ATM, and then the introduction of IP transport into the radio network, and then through to 4G, where we dropped the traditional circuit switch domain and we carried everything as IP packets and introduced more quality of service to differentiate services. And then, of course, into 5G. And I continue to work on 5G Advanced now. And I'm also involved with NTN now, non-terrestrial networking, to understand how we introduce a kind of space component into mobile networks in the future. So, it's been a fascinating career. Still thoroughly enjoying it, and really looking forward to talking about mobile backhaul.
Excellent. It's and it's interesting because when we think about 5G, because that's the dominant one right now, is we really think mostly about the air interface, RAN. And yet it's kind of like the unsung hero here, right? The transfer that makes it all possible, and sometimes is actually the bottleneck. So why don't you tell us what is the role and how should we think about it? Because what I think it's really emerging is that it's not just a pipe. Like I guess everything in wireless is or it is a pipe, but it's a smart pipe. It's not just a piece you just plug in and then it works. So why is it so important?
Absolutely. Well, if you look at a lot of mobile network diagrams, you typically find the RAN, as you say, with focus on the radio interface, the air interface itself, and then you find the core network. And between the two, you either find a thin line, or if people are feeling generous, maybe a fluffy cloud to imply there might be more than just a little line in there. And that tends to be called mobile backhaul or mobile xhaul. So mobile backhaul is actually a multidisciplinary field. It's quite a complex field, and it's absolutely critical, because you think about the amount of money mobile operators around the world spend on radio access networks and on RF spectrum. But it seems an awful pity to invest in all that infrastructure and spectrum and license fees that go with it, to then actually block traffic when it gets into the transmission network to prevent it getting to your core. So actually dimensioning that mobile backhaul is absolutely critical, and making the right techno-economic investment to connect the RAN to the core allows for optimal network performance, and it allows an operator to really sweat those assets, those cell sites that are costing money, that spectrum which is costing money, and of course the radio equipment deployed to support that as well. So it's very much a multidisciplinary field. And if we just maybe run through some of the key areas that mobile backhaul architects and engineers need to understand as they start to design and plan, then I think that will become quite obvious. So vertically, I mean, we've got the techno-economic at first. Everything needs to be modeled. We need to understand costs associated with the kind of playoffs. And of course, when I talk about correctly dimensioning a network, this doesn't mean just throwing lots and lots of capacity at it, because again, there's a cost to that. So yeah, yes, there's some statistical multiplexing required, but again, that needs to be done in a way that complements the radio interface. But then we have to think about factors like end-to-end performance, security, and authentication. So you often find IPsec is used in the backhaul segment. And then we've got a transport layer. Now within that transport layer, if for example we're using geostationary Earth orbit satellites, which are sometimes used in remote areas for backhaul, then we may want to do some TCP optimization. And then of course we come down then through the IP layers, maybe some MPLS in there, some carrier Ethernet, and then the underlying technologies which probably people associate more with backhaul, which is an optical fiber network, or a microwave or millimeter wave radio, or some satellite communications. And increasingly, of course, we're now seeing the use of LEO satellite communications as well, low Earth orbit, with a lower latency and higher data rate that brings. So that's kind of the stack from the top to the bottom. But then either side of that, there are some other factors that we need to understand and consider. We need to know the RAN configuration. So what is the radio network configuration in terms of number of carriers, channel bandwidth, what do you want to dimension for? What is the RAN architecture? And that's particularly important when we use the term xhaul, because xhaul implies it may be backhaul, it may be mid-haul, it may be fronthaul, or indeed, I'll even introduce the term side haul, which we'll explore a little bit later when we talk about advanced RAN coordination and inter-site carrier aggregation. So there's aspects of the RAN architecture and the RAN functional decomposition. And then there's the RAN protocols themselves and how the protocols behave over the network. And then alongside that, we've got the quality of service. I mentioned before, we don't have a circuit switch domain anymore for voice. So voice is all managed as data, and that data needs a particular quality of service to support real-time signaling and, of course, real-time media. We've got time and synchronization as well. The base station network has always relied upon frequency synchronization, so that kind of beat that keeps the frequency operating correctly. And that often comes from the network. Traditionally, on older networks, that would have been the HDB3 waveform, the 2 megabit signal that provided that clock in. Nowadays, it comes in typically via synchronous Ethernet, or it may be carried in IEEE 1588 as a PTP, precision timing protocol. And then we've also now got time of day as well. So we have to carry time of day, so very accurate timing for TDD transmission, time division duplex. And then on top of that, of course, we've got the capacity model itself, which we need to understand and evolve as capacity changes. So, hopefully that demonstrates just how multidisciplinary it is to really understand, design, and implement mobile backhaul networks.
And actually, as you were going through this, I just remembered that a few years ago I did the model of Open RAN, and trying to figure out where it is that you put the different components, the different RAN components, how centralized or how much should be centralized, how much at the edge. And the finding was that it really didn't matter the RAN equipment. The most important thing that mattered was the cost of the transport. Because it's the cost of the transport that, because obviously the more stuff you put at the edge, the more transport, backhaul you need, right? That's obvious. But if that backhaul is expensive, that defines that really is the biggest element. Just everything else just kind of like and that sort of goes to your point of like, you know, the backhaul frontal whatever that is just like a line or whatever. But people don't really talk about it. And in this model, because it came out to be an unexpected contributor,
Okay.
I just did a very accurate modeling of it instead of putting a number, which is what I would have done otherwise.
Yeah.
And when you start looking at that number, I mean, at what you realize that it's absolutely crucial, and it makes sense. I mean, it's, you know, when you think about it, why shouldn't it be so important? And yet we do, it doesn't really seem to sink in as much. And so, as you said, you know, it's not just having enough capacity to meet the RAN traffic, it's how you structure the whole thing. This is why it's multidisciplinary, because you have to put it in the context of your network. So maybe you can tell us how we, as we go through, you know, 5G and 5G advanced, which is pretty 5 plus, right? Standalone. How is that changing? How much more? Because we also gain more flexibility in how we deal with it. Is that right?
Yeah, absolutely. And we've got more options than ever now, particularly, I mean, you mentioned Open RAN, of course, but more broadly, if you look at the options for RAN functional decomposition, even within 3GPP, you know, we can take our 5G radio network and break that down into a number of RUs, our radio units. We can then decompose our base station, the actual baseband within the base station, into a DU and a CU, so distributed units and centralized units, as they're often called. And that's confusing terminology because the distributed unit can be centralized and the centralized unit can be distributed. So rather strange terms. As long as they appear in the right sequence, you can kind of put them pretty much where you want.
And also, if I might say so, I mean, it's not one or the, it's not a Boolean thing because it can be put anywhere in the middle. I mean, so what I'm saying is like the distance between on any of them, it's, you can choose and that depends also on the density of cell sites. So it's all, the whole thing is just like you have many variability parameters to choose.
Absolutely, and this is where network architects, you know, network designers really do kind of earn the money by finding the optimal techno-economic in terms of how to deploy that network. I mean, if you are decomposing the RAN, then there are definitely some considerations in terms of the latency budget between the RU and the DU. That typically, particularly if there's massive MIMO involved, that would typically limit you to probably about 20 kilometers of fiber distance. And that would typically be carried on fiber purely because of the capacity demands when you go to fronthaul. And of course, there are different models from CPRI to eCPRI to open fronthaul that have different requirements. And then, of course, your CU can go deeper in the network. But actually, what some of the things that constrain the position of the CU are things like radio resource control, radio resource messaging, and just how much latency you want to put into that process and how that impacts things like call setup and mobility procedures. So there's definitely considerations around latency and different factors considering each component. But if we just maybe go back to backhaul for a moment before we decompose the radio network, certainly as we've moved from 3G to 4G to 5G, we've seen a big shift from maybe cell sites with 100 megabits per second of transmission up to 4G, where we started to put 1 gig in as a standard building block. And then nowadays in 5G, we tend to find cell sites have a 10 gigabit per second connection. Now, cell sites today will not typically demand 1 gigabit per second of capacity because of the RF, assuming a typical 3-sector cell site with multiple spectrum blocks deployed. However, they will demand more than 1 gigabit per second. So of course, the granularity of carrier Ethernet, we go from 1 gig to 10 gig. It may well be you do some policing or aggregation or overbooking once you get into the core MPLS network, and you can do that quite safely. But we do tend to see that move from 1 to 10 gig in the access network now. There are a number of ways you can do that. You can deliver simply 10 gig carrier Ethernet based products on fiber, or you could deploy some kind of access DWDM, dense wave division multiplexing solution. And I'll talk a lot more about this during our conversation, because this is what's really enabled the advanced RAN coordination that we've introduced onto BT's EE network. But also this is the foundation for any future fronthaul requirements for a centralized RAN architecture. So Access DWDM is an interesting innovation. Traditionally, Access wave division multiplex intended to be CWDM, coarse wave division multiplexing, but as networks have grown up and DWDM has achieved a volume economic, then typically DWDM is cheaper than CWDM nowadays, which is not where it was maybe 10 or 15 years ago. So DWDM in the access space is now viable, and there are products available that support that, such as OpenReach OSA Filter Connect. And therefore, you can deploy a solution light a single wavelength at 1 gig or 10 gig, depending upon your capacity demand, but then have additional wavelengths available for other types of service, be that front haul or indeed some of the side haul type technologies we're adopting to support the advanced RAN coordination feature. So that's fiber, and that's fantastic. So we have a fiber first strategy. Wherever we can deliver fiber backhaul, we absolutely will do so.
Mm-hmm.
But where we can't do that, of course, we're still reliant upon things like point-to-point microwave radio systems, and in some cases millimeter wave radio. Now, strictly, any radio system over 30 gigahertz is millimeter wave, but if we think about industry parlance, we tend to talk about microwave systems up to maybe 42 gigahertz. And then when we talk about millimeter wave, we're generally referring to E-band radio systems today. So 71 to 76 paired with 81 to 86 gigahertz. And those systems allow us to do significant capacity, up to 10, even more gigabits per second, but over relatively short link lengths, maybe 1 kilometer to 2 kilometers. But the great in urban areas where, for example, you may have a fiber to one particular rooftop, but then have a real challenge getting access through a building to put fiber on an adjacent rooftop, where you could actually just extend that connectivity via a millimeter wave radio. The challenge then, of course, is if you want to move from backhaul to front haul, you won't have enough capacity on that radio system. So that can be quite challenging. And that's assuming you've got the typical kind of carrier configuration you'd expect on an urban macro cell.
Let me ask you one thing though. So
Sure.
the wireless backhaul seems to be more like at the extremes, where you are in extreme dense environment where you might have fiber in the ground, but you just cannot reach the cell site, or in rural areas where there is no fiber. Is that
absolutely? And yeah, completely. So it's used by exception in urban areas where you just can't get the fiber, typically not because fiber is not available in the area, but generally some kind of way leaves or planning type issue prevents you getting access to fiber. But absolutely, you're perfectly right. In the more rural locations, we use microwave extensively, and we have thousands of microwave radio links in the EE mobile network still, and we expect to have thousands in the end game, purely because of the location of some of these rural cell sites. So it may well be there's fiber running past on the main road, but then getting that fiber to the top of a hilltop could be hugely expensive. So microwave's got a massive role to play in those areas within the mobile network. But again, we need more capacity and we need greater link length. And actually, those two kind of play off against each other, really. Typically, the way you introduce more capacity is through wider radio channels or higher order modulation schemes, for example. But actually, that then impacts your link budget, which means you get a shorter link for a given frequency band, transmit power, antenna size, etc. So that pushes you into lower and lower microwave spectrum where there's less capacity. So that constrains capacity, but you get the link length and the availability. So again, microwave radio engineering in this context is a fascinating topic because it's a real intersection between physics, electronics, and mathematics. And you need to consider all of these factors in building that microwave network. But then if we look beyond microwave into very, very remote areas where you don't have terrestrial transmission at all, then this is where we're seeing the growth in satellite backhaul. We do use satellite backhaul in some remote locations. We also use it for resilience as well in some scenarios where we back up a fiber or back up a microwave with a satellite hop. But let's just touch on the primary use case, which is providing satellite coverage to remote areas. We used to use geostationary Earth orbit satellite. That was the norm at the time, of course. The challenge with that was capacity was relatively limited, but latency was quite considerable. So typically anywhere between 650 and 700 milliseconds round time trip, practically, by the time you introduce the terrestrial component as well. And that meant we had to do all sorts of clever things with TCP optimization. It wasn't particularly user friendly, etc. So more recently, we've been working with LEO satellite providers, so both Eutelsat OneWeb and Starlink, to understand what can we do with LEO, because LEO gives significantly higher capacity. And also it offers significantly lower latency to such an extent that somebody wouldn't realize they were on satellite backhaul versus microwave or fiber. So, it really is indistinguishable from terrestrial transmission from that performance perspective. So it meets all the criteria for real-time voice and real-time video communication, and of course capacities somewhat higher as well. But still, it's definitely a hierarchy. Fiber first, terrestrial microwave second, then if we have to, we use satellites. And then of course the overlay case is satellite for resilience as well.
Yeah, so basically you have everything covered, because once you have satellite and fiber, I mean, basically any place on Earth, well, or in the UK, for in your case, is covered. So the question is, well, how you decide among those, and so it becomes more of an issue of management, and that's where ARC is coming in. Because there, and maybe you can tell us more first what it is. You're basically using a different way, fundamentally different way to manage it. This whole complex. So you have to decide what to use, but then the second question is like, what is the best way to manage whatever capacity you have on the ground? Right.
Absolutely. And this is where we were absolutely delighted to deliver the world's first implementation of advanced RAN coordination. Advanced RAN coordination is an Ericsson feature. So we work closely with Ericsson as one of our 2 base station suppliers. And that particular feature allows us to implement inter-site carrier aggregation. Because when we move to 5G SA standalone, we don't have the ENDC, EU to New Radio dual connectivity features that we had in NSA, non-standalone. So there is no dual connectivity. So the only way to achieve the kind of capability we want is to implement inter-site carrier aggregation. And that's in a scenario whereby we have a streetworks, for example, a small physical structure that maybe has 1800 and 2100 megahertz spectrum deployed. And then we have let's say, for example, a large rooftop that has the whole range of spectrum bands right the way up to and including massive MIMO at 3500, plus a lot of spectrum at 2600 as well. And that's covering a large area. Now that smaller streetworks type site, street column, would have been deployed traditionally for capacity infill. You may get a bit of additional coverage from it as well, particularly in building, but primarily it's there for capacity infill. But to actually put massive MIMO and 2600 on there as well, you may need to upgrade the structure. So actually, how do we optimize the accessibility of those higher frequency bands, which are clearly visible because the site density in urban areas is so great? We do that by actually opening up inter-site carrier aggregation. And this is where ARC comes in. So simple in concept, but the practical realization really relies upon your access transmission. And this comes back now to the point about access DWDM, where our mobile backhaul continues to operate as normal. So each of the 2 cell sites that make up that inter-site carrier aggregation group will have their own backhaul. But of course, a UE can only be connected to one core network connection at a time. So therefore, one of these sites will provide the connectivity. So if we push the user onto the higher frequency bands, which we always try to do, where we have most capacity, and then the user's generating significant traffic, so we want to connect them to the local cell site for the 1821 because it's closer, we'll have a much better performance, and therefore you'll get a higher modulation and coding scheme for the user, so greater capacity. Then to do that, we have to forward some of that information that comes on the backhaul from the rooftop macro cell to the streetworks site. And the way we do that is we introduce a connection, a logical connection between the 2 base stations. That's based upon the Ericsson E5 interface. But of course, the practical realization is the base stations are not physically connected together. They connect back to the core. So we have to route back to the core and then switch that traffic back around to the adjacent base station that takes part in that ARC carrier aggregation pair. And we do that by lighting additional wavelengths on the Access DWDM product directly. So we come straight out of the baseband on a colored optical transceiver, plug it into an appropriate channelized filter on the DWDM. That goes back to a central location where we do some very, very high speed, very simple layer 2 MAC switching. And then we switch that back out to the adjacent base station. And what we're actually carrying there is PDCP packets, packet data control protocol packets. So these are already encrypted and protected, and they're just carried over that link. But because of the way the radio operates, we've got a very, very tight latency budget. So we have to do all of this within 350 microseconds RTT. So of course that puts some physical limits on the distance of fiber. But again, as a network architect, a network designer, you build that into your model. You understand, the relative techno-economics, which you talked about before, as one of the key requirements for building great xhaul networks, and you build that into your solution and deliver it. So we have that up and working in the network. It's rolling out more extensively within the urban areas across the UK at the moment, and we're seeing a significant uplift in user performance. So really, really encouraged by that feature. And this really is a first stepping stone towards starting to explore some of the features that we could see from a centralized RAN in the future.
I would say it's more than a feature. In a sense, well, I mean, it is obviously technically a feature, but it's conceptually a big step forward, because you're basically managing traffic across cell sites, because traditionally every cell site is its own kingdom, does whatever it needs to
island do. Absolutely,
now that is kind of so. On one hand, you have the sort of move towards openness, where everything can be separate in a way, and act independently. But this is also moving a little bit in the opposite direction, which doesn't mean that it's not compatible, but it's a different trend in terms of trying to organize at a sort of more general level. I mean, a higher level. Because you realize that not cell is on its own, so you can get much more efficiency in the overall network if the adjacent cells coordinate with each other. But obviously they can't coordinate. I mean, you need to go kind of move backwards. And so what does that mean? Because then, the cell side it kind of loses its independence in a way.
Yep.
And then obviously you need to have the right transport, otherwise this is just not going to work.
Completely, yeah. Having the right strategy, deploying a fiber first strategy, and deploying the right products on that fiber, Access DWDM being the example, is the enabler for a lot of these things, because the additional wavelengths were simply there and available. So the cost to bring this to market from a transmission perspective was minimal. And again, back to that techno-economic, which sits across all the work we do within networks. So in addition, it also lays the foundation for, as you say, for this wider integration of RAN functionality. And that's when we move to a more centralized radio access network architecture and start to implement fronthaul. So we separate the radio unit from the baseband, from the DUCU, and we move the fronthaul, that digitalized radio signal, over that connection. Now, typically that will be eCPRI and or open fronthaul moving forward. So, a kind of real-time variable bit rate stream carried over there, but again, significantly higher capacity. So very dependent on having that fiber and those wavelengths available to connect those units together. But if we do that, not only do we then have another way of implementing the carrier aggregation that I've talked about, the intersite carrier aggregation, but also there's a whole range of new features around coordinated multi-point transmission and reception, for example, that we can introduce as well. And we really do then move away from the cell sites being islands in their own right to having effectively a cell-free architecture. We have a large geographical area under the control of a single baseband unit or DUCU. And then that baseband unit can make real-time decisions on how beams, for example, across massive MIMO transmit. And when we think about massive MIMO, traditionally we've thought about TDD at the 3.5 gigahertz band, but increasingly we're seeing FDD based massive MIMO now as well for 18, 21, 2600 megahertz. And that gives, again, another capacity uplift in the network, which is vital. We start to see improvements in spectral efficiency. And if we can then use that centralized brain, that centralized baseband unit, to make real-time decisions as to which beam transmits to which user in which direction at one point, then we can really start to lift that cell edge condition, because cell edges have always been challenging because of interference. But actually, if we can switch off interference, on a millisecond by millisecond basis within that transmission time interval, for example, then we can actually improve the modulation and coding scheme at any given instance for a user in that environment. So again, we uplift the whole capacity across the network by increasing that spectral efficiency. So there's lots of really clever stuff we can start to do in mobile networks if we have the right mobile xhaul solution in place. That becomes the enabler. And by putting access DWDM in, you remove a lot of the barriers to entry, and it's a fairly low cost evolution then from a distributed RAN to something like intersite carrier aggregation and or centralized RAN in the fullness of time. So we're definitely moving in that direction. So it's pretty exciting. Yeah.
So it's a combination of having a cell-free architecture, and then you basically is TDD, FDD. You can use massive MIMO. I mean, because those have been all kind of issues that were kind of limiting your ability to have a efficient RAN. Now, I guess that I would say that the cost there, however, from the BT side, is that you need to make sure that the backhaul, or the fronthaul in this case, is more. So you need more of an investment in that area to make sure that everything else is enabled. Otherwise, everything falls apart.
Completely. But that investment is not significantly greater than just putting a 10 gig in. And then the incremental cost of enabling that additional capacity is quite minimal. So the business case for the advanced RAN coordination and the intersite carrier aggregation, what was compelling, because we had the enablers in place. Had we had to go out and buy additional 10 gig circuits rather than just lighting 10 gig wavelengths by buying new optical transceivers, it would have been a very difficult business case. So again, it's about really understanding the strategic direction of the radio access network and then making the right decisions around that broader techno-economic when you look at the network, not only today, but actually in 3 years, in 5 years, in 10 years' time. What is that direction of travel, and how do you optimize that total cost of ownership?
Yeah, now this is a very tight optimization process. Understandably, it's really complex and it's absolutely fascinating. But also, as I said, this is a Ericsson solution. Other vendors are working along similar lines because clearly there is a huge opportunity here. But doesn't that also limit the amount of openness you have? Because if you have a RAN where you have 3 different vendors in contiguous locations next to each other, that would be much harder, if not impossible, to implement. So is this a trade-off there?
There is to a certain extent. I mean, just for clarity, the intersite carrier aggregation, the ARC, is an Ericsson feature, but of course, the wider conversation we had about centralized RAN is not specific to Ericsson or any other vendor. That can be implemented with any vendor. It can be implemented using Open RAN equipment and Open RAN principles as well. But there is a huge playoff, without a doubt, between openness and closed systems, and it's a really valid conversation. We're definitely seeing more openness now. We're seeing the major vendors all supporting third-party radio units, for example, and we're seeing more and more examples of that integration. We're seeing the option to host vendor DU/CU equipment on third-party compute as well, increasingly as we see cloudification of the RAN, the use of x86, typically with some kind of accelerator today. But also, of course, the magic ingredient in a lot of radio access network is the scheduler and the scheduler itself. So if you want that scheduler to work across multiple vendors in a fully open way where there's no systems integration required to get it to work together, then you are going to compromise a little bit on the performance you can achieve, and that's going to impact your spectral efficiency. So again, there's a balance to be struck, absolutely. Operators have always been keen on openness, but there's definitely a balance to be struck to understand what gives you the optimal performance and where you should be open and where maybe a proprietary optimized solution is the best path for a particular implementation.
Yeah, absolutely. And I think you're striking a very good balance here in a topic that it's kind of like often discussed with religious tones. It's like
Yeah.
you're on this side or the other side, but clearly there is an advantage to be a little bit closer or a little bit more open. I mean, it's just like it's not a rand thing. It's just like everywhere in life, right? I mean, the more openness you have, the less efficient you're going to be. And the question is that where is the right balance?
Yes, indeed.
It's unavoidable, but it's a good conversation to have rather than just stick to the extremes. You want to be in the middle. You don't want to be one way or another.
Absolutely. And as a network architect, it's absolutely essential, because primarily what I have to deliver and my team deliver is that optimal techno-economic. So we've really got to understand all the technologies, the standards, the different vendor positions, but then see how that delivers what the business requires. And that's really, really quite key. So that does require lots of iteration in terms of planning, design, and development. We spend lots of time on whiteboards when we're developing these new concepts. But fundamentally as well, it's about finding the optimal price point to deliver that capability into your network.
Yeah. So you're rolling out Arc throughout the UK, right? Is that you started already, but yeah.
Oh, absolutely. It's live in much of the UK now and continues to be rolled out. It does rely on overlapping coverage. So it tends to be something that offers most benefit in the urban areas, less of an issue in rural areas, but then you don't tend to have the same capacity challenges in rural areas anyway, to be honest with you. So there'll be less of a use case there. So yes, absolutely.
Yeah. Final question.
Yeah,
we cannot have a podcast if you don't talk about AI, right?
Absolutely.
How is AI, or is AI changing the requirements on backhaul, fronthaul, xhaul?
Yep, that's a really interesting question. I guess there's two ways of approaching that. Firstly, how is AI impacting the network itself? In terms of providing additional capability to monitor the network, to proactively respond to faults, to switch traffic, etc. And that's something we're working very, very closely on. Of course, when we talk about centralized RAN, that centralized brain within the BBU, DU, that's very much going to benefit from AI capability. And we're having lots of discussions about what AI RAN could look like now, and making those real-time decisions about scheduling and optimization, beamforming, feedback, etc. So that's really quite key. But then on the opposite side, of course, what does AI mean in terms of generating traffic into networks? And then what will that look like? At the moment, we obviously see continued data growth. That data growth has slowed a little, but it continues to grow year on year. We're not seeing a huge volume of traffic that you can say that is AI and that's going to change the world, to be honest with you. I mean, clearly the dominant type of traffic on our network is video today. So we're seeing lots of video traffic in the network, of course, and that's very downlink heavy as people pull content. But absolutely, the key thing is to have a network that can support AI, and the underlying ingredient for that is capacity and performance. So if you've got the coverage, you've got the capacity, you've got the suitable performance in terms of acceptable latency, and latency which is bounded, so you don't get massive latency variation through bad quas design or bad capacity dimensioning, then you can support a whole range of applications on top of that network.
Absolutely. Well, Andy, thank you so much. I've learned a lot, and I'm sure our audience have learned a lot about the latest in xhaul. And I think that the work you're doing is absolutely fascinating, because this is like it opens a new dimension, as I said, way more than a feature. So thank you so much for sharing your thoughts with us today.
It's an absolute pleasure. And anytime, Monica, it'd be lovely to talk again. There's lots to talk about. Thank you.
We should do another one soon, once you have everything covered. Okay. Thank you so much. Bye-bye.
Thank you. Take care.